Howdy, this is your friendly neighborhood physics teacher here, going to help you review for your final exam. So this will be the last video I'll be making for y'all. Hopefully you've enjoyed them. But right now, what I would like for you to do is grab your spring semester final review, and I'm going to go over some questions that I think that would help you on your final. Now, just because I don't go over the question doesn't mean there's not going to be a question like that on the exam. I'm just hitting some key points, okay? Just want to make that clear that was in the video doesn't mean it's not on the test. I'm just going over some key points. So, of course, your past test will be very helpful. Watching past videos, they're still up on Schoology. Physicsclassroom.com is always a good help. I've posted throughout the semester, I've posted a lot of different helpful links, and then I have notes, of course, and then past worksheets are always going to be very, very helpful. So first thing I would like for y'all to look at is your equations, okay? Looking at your equations, you will be given the equations on the test, kind of this similar setup that's on your review. But knowing what equations, what letters go with what equations is extremely helpful. So please, I'll post the key to the review, but please look at your variables, names, and units. This will help you a lot. I did realize I forgot two that need to be part of the chart. They are on the key to the review. So one's at the top, one's on the bottom of the second set of notes, but I'll go ahead and write them down here. So delta U, that is your eternal energy. And that is measured in joules. The other one that I missed was little c, which is your speed of light. Big C is your specific heat. That is measured in meters per second, but that's also a constant. So remember, your speed of light is 3 times 10 to the 8th meters per second. So there were two things that I forgot to put in the variable list. So now what I'm going to do is I'm just going to go over a few questions that I think would be helpful. And I'm just going to go in order that they are on the review. So the first one that I would like for you to look at is number 1. So looking at number 1, it states, how would you describe the motion of an object that has balanced forces acting on it? So let's find an object that has balanced forces. So that means the force of gravity going down, the force of normal going up are equal. That means that if there is a force applied, there is a force of friction trying to slow it down, and those are equal. So all the forces are balanced. That's what that means. And there's a little click that says, pick all that applies. So that should give you a really clue that there's two answers there. Your two answers are actually B and C. So it can either A, be not moving, or C, moving at a constant velocity. Now, the not moving seems obvious, right? It's balanced. The object is not moving. Now, constant velocity is the one that a lot of people still have trouble with. Basically, think about if it's constant velocity, that means your acceleration is 0. If your acceleration is 0, that means your net force is 0. That doesn't mean there's no force there. It just means your net force is 0. That means in this case, in the x direction, your F net and the x direction is your applied minus your force of friction. But if these are the same numbers, that's just going to give you a 0. So if you see a net force at 0, all that's telling you, it could either A, be not moving, or B, or in this case, B, not moving, or C, moving at a constant velocity. So that's a very concept that people are still having trouble with. I wanted to make sure I went over. I'm going to jump now to number 6. So looking at number 6, you have a box, and you have some arrows coming at said box. So the one going down is 6 newtons, we have 5 newtons, we have 6 newtons, and we have 5 newtons. So, first thing you need to do is realize that these forces go together and these forces go together. They cannot interact. So you have a 6 is going one way, 5 is going the other. They're going in opposite directions, so you end up subtracting. So you get 6 minus 5 gives you 1 newtons, but that is to the left. And then up here, again, you have 6 minus 5 equals 1 newtons, and that is to the south. So you have one going to the south, one going to the left. So whichever one, you can draw either one first. Let's draw the one going down first. But if you draw your one going to the left, you have to start where you finished drawing your other arrow. So it has to go from head to tail. It can't go from head to head, tail to tail. It's got to go from head to tail. Because then you can draw and you know exactly which direction your resultant vector is going. So, and this is the angle. If you need to find an angle, that's the angle you're looking for. So, this one's 1, this one's 1. You're looking for your hypotenuse, which is your resultant force. And so you'll end up doing a squared plus b squared equals c squared. So 1 squared plus 1 squared equals c squared. 1 plus 1 equals c squared. 2 equals c squared. Take the square root, and you get c, which is the square root of 2. And you could take that a step further, pulling out my calculator. And you end up getting 1.4. So your C ends up equaling 1.4 newtons. That's your resultant force. Now, the direction it's going, if you think about your never eat soggy waffles or never eat sour watermelons or whatever little thing comes from, I always remember it's north, south, and then we. So, however works for you, you realize this is going it's going in the southwest direction. And actually, this is not number 6. I realize this is number 7. I'm working. I do apologize. Number 7. So, and it's going in the southwest direction. So, there you go. Just want to make sure you knew how to do that one. Let me scroll here. What's another one? Let's look at number 10. So, number 10. Let's see here. Let's read it. A 90-kilogram hockey player is skating east on steel skates. The coefficient of friction is 0.02. The force of friction on the ice is, so we need to find force of friction. So we look at our equations. We see that force of friction equals mu times your normal force. We know mu. So let's start with our givens. So let's see what we do have. We have mass, which is 90 kilograms. We have mu, which is 0.02, no units. And we always have the acceleration due to gravity, is negative 9.8 meters per second squared. And we're looking for the force of friction, but we need the force of normal. Now, if you remember, an object is horizontal, force of gravity, force of normal are equal. So, unknown is force of friction equation. So, we know that force of normal equals our force of gravity, but force of gravity also equals mass times acceleration due to gravity. So therefore, our force of normal equals mass times acceleration due to gravity. And we have all those given. So our mu is 0.02, our mass is 90, our acceleration due to gravity is negative 9.8. So therefore, the friction of the object is negative 220.5 newtons. Remember, the negative just means which direction it's going, so that's just telling you it's going to the left, or in this case, west. Because it said he's going east, so therefore he's going west. And that is our answer. So, next one I would like for you to look at is number 11. 11 is a very tricky one. So we have a box that's going on an incline, and we have the angle. The angle is 25 degrees. And another thing we have mass is 150 kilograms. We have the acceleration also, which is 2.3 meters per second squared. So those are some key points. Biggest thing to help you on this is to do your free body diagrams. So force of gravity always goes straight down. Force of gravity always goes straight down. So now you have your force of normal is always perpendicular to the surface. And you know you have force of friction because it's labeled there. So you have the force of friction keeping the box on the ramp. So those are our three big forces. Now, because we like to make life easier, we're going to kind of change up our frame of reference. So everything that's going in this direction is going to be your x. Anything going in this direction is your y. So therefore, our force of gravity is now at an angle. So we have to break it down into its x and y directions. So, and through the magic of geometry, this becomes our angle. So, we have to figure out what our force of gravity is. Our equation for force of gravity is mass times acceleration due to gravity. Our mass, acceleration, so that's something we always have. We have acceleration due to gravity. And you plug that into your calculator, and you get this lovely answer. So, that's our force of gravity. Now, we can use this force of gravity and break apart in our x and y components. So now, we know that this is our hypotenuse, this is our angle, so that's adjacent, and that's our opposite. So to find either ones, let's do our force of gravity in the y. That's going to end up being our cosine, because it's adjacent. Cosine theta equals adjacent over hypotenuse. So you can plug in your information there. Our adjacent is our force of gravity in the y. Hypotenuse is our force of gravity we just found. We want our force of gravity in the y to be by itself. So the opposite of multiply is divide. Multiply divide is multiply. Just flip it. So then you get your 1470 times cosine of 25, and that gives you 1,332.27 newtons. And if you notice that I kind of did it in the same color, and the reason I did that is because if you think about your net force in the y, is it moving in the y direction? No, it's not moving in the y direction. So the key thing is, so if it's not moving in the y direction, you know that either your forces have to be equal. Everything going up has got to equal everything going down. So you know that your force normal equals that. So now that you have your force of normal, we can solve for our force of friction. Force of friction is just no, not force of friction yet because we don't have our mu. So let's do our force of gravity in the x. So sine theta equals opposite over hypotenuse. It's 25. Our opposite is force of gravity in the x. Force of gravity is our 1470. Again, we want our force of gravity in the x to be by itself. So the opposite divide is multiply. And what you do to one side, you got to do to the other. So you plug that into your calculator. And you get 621.25 newtons. And there you go. So now you can find your force of gravity, or force of friction. And you have to do that by doing your net force in the x direction. So your net force in the x direction equals your mass times acceleration. You have mass, and you have acceleration. But your net force also equals your sum of the forces. So let's look at how many forces are in the x direction. Well, we have two, force of friction and force of gravity. So force of gravity in the x minus your force of friction. And since that equals, you can move that over there times your acceleration. So now we have everything but force of friction. So we want force of friction by itself. So this is a positive, so the opposite of that is a negative. So you bring that over, and you have a negative force of friction. It's MA minus your force of gravity in the x. To get rid of the negative, you can divide both sides by -1. So then you get your force of gravity in the x minus your MA. I just flipped it because that becomes positive, that becomes negative. And you plug in what you got. So force of friction, your force of gravity in the x was 621.25. Your mass was 150. Your acceleration was 2.3. So then you get your force of friction to be 276.25 newtons. And your net force, go back here, it's just your mass times acceleration. And so that gets you to 345 newtons. Net force in the x direction, because your net force in the y direction is 0. Now, key thing here is which ones are your main forces. So your force of friction is a main force, your force of normal is a main force, and your force of gravity. Your force of gravity is a main force. So those are your main forces. Your force of gravity in the y and force of gravity in the x are your broken up x and y components. So those aren't really main forces. Whew, so that was a big one, wasn't it? Whew. Another big one is number 12. I'll go ahead and work that one out for you. It kicks people's butt also. So again, you have force of gravity going down. You have a force applied. That equals 60 newtons. And it's being pulled at an angle of 30 degrees. You have a force of normal going up. and you have a force of friction going to the left, and they were kind enough to give you that your mu is 0.3. So, and we have to find all kinds of stuff with this one. So, let's always start with your force of gravity, and then go the direction of where you have an angle. So your force of gravity is just mass times acceleration due to gravity. Your mass of this block gives you, it's 10, so a negative 9.8. So you get a negative 98. Remember that negative just means it's going down, okay? All that means, it's going down. Next thing you need to do is break your force applied into its x and y components. So this is your hypotenuse, which is your 60. This is opposite, that's adjacent. So you can solve for your force applied in the y using sine. Theta equals opposite over hypotenuse. Sine of your angle. Your opposite is your force applied in the y. Your hypotenuse is 60. You want your force applied in the y by itself. So you get 60 sine of 30. And you get 30 newtons. And then to do your force applied in the x, you'll be using cosine, which is opposite over hypotenuse. Your angle is still 30, but your adjacent is now force applied in the x. Hypotenuse is still 60. Multiply both sides by 60. So you get that your force applied in the x equals 60 sine of 30, and that's when you get 51.96 newtons. So you keep going around, you do your force of normal. Now your force of normal is kind of special. Your force of normal, you have to figure it out a little bit differently, because we have two forces going up and one force going down. So your net force in the y direction is still 0. So again, that means everything going up has got to equal everything going down. So our force of normal plus our force applied in the y is going up, and then our force of gravity is going down. And you want your force of normal, so your force of gravity minus your force applied in the y. And so that gives you 98 minus, 30, which gives you 68 newtons. Now that we figured that out, we can go to the force of friction. Remember your force of friction equation is mu times normal force. Force of friction, and we just figured out normal force, which is 68. And so therefore your force of friction is 20.4 newtons. So that's mainly the thing you'll be solving for. You can take it a step further and solve for net force. So net force in the x direction equals your mass times your acceleration. Or it can equal the sum of your forces. We don't have acceleration, so let's use the sum of the forces. How many forces are in the x direction? Well, we have a force applied in the x. It's trying to pull it, and you have your force of friction. So force applied in the x is 51.96. Force of friction is 20.4. And that gets you to be 31.56 newtons for your F net x. And then now we can solve for our acceleration. meters per second squared. Do-do-do-do. So if you notice, we started, okay. So we started with force of gravity. We went to our force applied and did our, break it down to its x and y components. Then we went into the force of normal. Then we went to friction. And then we solved for our F net, and then we solved for our acceleration. So we kind of went in that little circle there. So there we go. The next one I think I'm going to do is 16. 16, two students are sitting 1 meter apart. One student has a mass of 60 kilograms. The other has a mass of 95 kilograms. What is the gravitational force between them? Anytime you have two objects and you're trying to find the gravitational force between them, you're going to use Newton's universal gravitational law equation. If you remember that your g is a constant, and that constant is 6.67 times 10 to the negative 11. And it gave you your two masses. It gave you one mass to be 60, gave you the other mass to be 95, and it gave you the distance between them to be 1 squared. A couple of hints on this one. Remember that when you plug it into your calculator, you can do the 6.67 capital E. That's your second double E, negative 11. I put parentheses around that. So you can plug into your calculator like that. And I would make sure I put parentheses around my 1 squared after I divide it into the calculator also, just to keep everything together. If you plug that into your calculator, you get 3.81 times 10 to the negative 7 newtons. So the most tricky thing about this is the fact that you have to plug it into your calculator. Now remember, there's some key things on this one on relationships. If one of your masses go up, your force of gravity goes up. If your radius goes up, your force of gravity goes down, and vice versa. So your mass and your force of gravity have a direct relationship, and your radius and your force of gravity have an inverse squared relationship. So I would know that. A handy thing to know. So now I'm going to jump to 23. So 23, a track star in the long jump goes into a jump at 12 meters per second and launches herself at 20 degrees above the horizon. How long is she in the air before returning to Earth? So we have a velocity at an angle. Anytime we have a velocity at an angle, you have to break it into its x and y components. You have to break it into your x and y components. So this would be your velocity in the x, this would be your velocity in y initial. And again, this is hypotenuse, opposite, adjacent. So you would use sine, opposite over hypotenuse. Sine of 20 equals your opposite is your velocity in the y initial. And you plug that into your calculator and you get 4.1 meters per second. If you're going to solve for your velocity in the x, you would use cosine, adjacent over hypotenuse. So cosine 20, velocity in the x, hypotenuse is 12, multiply both sides by 12. And that would get you that gets you to be 11.28 meters per second. So that'll get you your velocities and your initial velocity in the y and your velocity in the x. So this one's asking for time. So there's actually a couple of ways you can do to solve for time. The first way you can do is using this equation. Plus GT. Using that equation. So if you remember how your projectile works, so your initial is the same as your final. So you know your final, and it's just going to be negative because it's going down, so it'll be negative 4.1 equals 4.1 plus acceleration due to gravity. Remember, it's negative because it's going down. And so you bring that over. You cannot add those two or subtract those two because of this. So you have to get this to the other side. And that gives you a negative 80.8.2. You want time by itself. So that gets you a 0.84 seconds. So that's one way to solve it. Another way to solve it that's the main way to solve it. So that's your time. Let's say we wanted to solve for our height as well. I'm adding some things to this problem. Let's say we wanted to find our delta y. So since we just solved for time, we can actually use y equals vy initial times t plus 1/2 g t squared. We can actually use this equation. Our initial is 4.1, our time. Now, key thing about our time though, on this one, key thing about our time is when does max height happen? Yes, mine happens at half time. So we would have to take this time and divide it by 2. So we need half time. So divide by 2. And that would get you 8 divided by 2. That would get you 4.2 seconds. So that is our half time. So that's what we need here. So we plug that. Don't forget your negative. It'll throw you off if you don't. 0.42. So now we just plug that into our calculator. So that gives you 1.722 minus 2.058. And remember, the negative just tells you direction. So you get a negative 0.336 meters. The negative is just telling you the object is going down. So you don't necessarily have to put the negative there. The negative is just direction. So that's your height. And then if we wanted to take it a step further and solve for our x direction, that's our Vx times time. So this one we would use our full time. So we solve for our V of x. Our V of x is 11.28. Our time, make sure you're using full time, because think about your distance happens at full time. And you plug that in. So 11.28 times 0.84. and your distance is that in the x direction. So that's just all the little things that can happen at a projectile at an angle. So let's do 24 because that's a projectile at the horizontal. So we have a model rocket flies horizontally off a cliff with a velocity of 50 meters per second. So it says horizontally, so that means that its velocity in the x is 50. If the canyon below is 100 meters deep, so that is our y, 100 meters deep, how far from the edge of the cliff does the model rocket land? So we are looking for our, how far means our x, our delta x, how far. So our equation for delta x is Vx times time. Well, we have Vx, but we don't have time. Remember, the biggest factor of time is height. Height is the biggest factor of time. So this is at a horizontal. And if you remember, your velocity, initial velocity of the y is 0. So we can take off the first part of this, the equation, and just use the second part. So we have our height, which is 100. 1/2. Remember, our gravity is negative 9.8. The model rocket is going down, so it's a negative 100, because remember, it's just direction. We're trying to solve for our t. So that gives us a negative 4.9. T squared is being multiplied. So we divide that gets us 9.8. So that gets us to be 10.2. We square root that. And that ends up getting us 2 seconds. Not 2, sorry, this should be 20. That's what's throwing me off. I'm like, what's going on here? Okay. That is wrong. Let's try that again. The funds of calculator. Always double check yourself. So now we take the square root of that. Like that didn't look right. And now we can plug our time into this equation. Our v of x is 50. Our time is 4.5. And we get 226 meters. This is why the other part, that's why you don't do calculator on your phone. So, now we're going to jump. Let's see here. What's the next problem I would like to do? Yes, I'm jumping to 64. So, problem 64. So, when doing a chin-up, a physics student lifts her 50 kilogram body a distance of 0.25 meters in 3 seconds. What is the power delivered by the student's biceps? So let's write down our givens. So we have mass, which is 55 kilograms. Our distance is 0.25 meters. And our time is 3 seconds. So That is our givens. We're looking for power though. Power is work divided by time. So we don't have work though, but we can find work. Work, work equals force times distance. But we don't have force. But we can break force up even more. Force is mass times acceleration. There we go. So make sure you don't get mad doing this problem. So we have mass. We have our acceleration. In this case, since it's being picked up, our acceleration is acceleration due to gravity. And our distance divided by our time. So our power ends up being 44.92 watts. So you can do it this way. If you look at the way I did it on the review sheet, I did it in separate parts. I found force, then I found work, and then I found period. Or you can just combine it like this if you know the formulas. So either way works. Next one I'm jumping to is 72. So 72, a box pushed at with a net force of 200 newtons for a distance of 9 meters. What is the work done on the box? So again, let's write down our givens. Force, distance. So work equals force times distance. So guess what? You just multiply the two. Yay! Woohoo! Work is in joules. There you go. Pretty simple one. Next one I'm going to jump to is 75. So 75 is a little more complicated than one of the ones on your test, but I wanted to go over it because it deals with an equation. So brass is an alloy made of copper and zinc. A 0.59 kilogram brass sample at 98 degrees Celsius is dropped into 2.8 kilogram of water at 5 degrees Celsius. If the equilibrium temperature is 6.8 degrees Celsius, what is the specific heat capacity of brass? So the first thing you need to know is since they get to equilibrium, your change in energy of the two are going to be the same. So your change of energy of your water is going to end up going to be the same as your brass. That change in energy is your thermal energy. So you can solve for your thermal energy of water, and then you can find the specific heat of the brass. So your change of energy or your thermal energy of water, you'll just do your MCAT equation. So your mass of your water is 2.8. Your specific heat of water is 4.18. And remember, your change in temperature is final minus initial. So your final minus your initial. So you're going to end up, plug that into your calculator. You're going to have that. So now you can use that to solve for your specific heat of your brass. So you have 21.07 equals your mass of your brass. You're looking for the specific heat, and it's your final minus your initial. The key thing to remember, though, is that because your brass is losing energy, that is going to be negative. And go ahead. And the reason that matters is because your change in temperature is going to be negative. So that's why that matters. You can go ahead and multiply these two numbers together to get 53.8. You want your specific heat by itself, so you multiply both sides by your 53. Remember, it's negative, sorry. There we go. So then your specific heat ends up equaling 0.39 in the joules per kilogram degrees Celsius. I would just focus on this part if I were you. The next part I want you to look at is your 78. I'm not going to do all of it. You can look at the key. I'll do one at each one. Like I'll do one example of each one, and then how to solve for it, and then talk about some key points about the roller coaster. So we have a roller coaster. Its mass is 100 kilograms, and this one does have a starting initial velocity of 2 meters per second. Now, a couple of things with the roller coaster is, remember, in perfect physics world, okay, so in a perfect physics world, you cannot get, this is where you start, you cannot get any higher. So at this point in time, at this big one, that's as far as your roller coaster can go without putting into energy. So this, when you're about to hit and you hear that and then you start going up, that's the point in time probably would drop it a little bit lower, but this is the point in time that they would have to add energy into the system, and it's because it's going to a higher hill. So as long that if you start at this hill and you want it completely with gravity, you cannot make it go a higher hill without adding energy to the system. So that's when they have to start adding energy. Just a couple of key points. So let's solve for our potential energy. Our potential energy equation is mass times gravity times height. Our mass is 100. Acceleration due to gravity is 9.8, and the height of our first one is 20 meters. Your chart here did get messed up. Your height is randomly with your kinetic energy for some reason, and then your labeling your hills is randomly with your potential energy. So just mark those off by itself. I do apologize. And so then you plug that into your equation or into your calculator, and you get that. Yay, yes, it's that simple. Your kinetic energy is 1/2 mv squared. So your mass is 100. In this case, our velocity is 2. So then you plug that into your equation, and you get 200 joules. Your mechanical energy, or your total energy, is you just add up your potential plus your kinetic. And so in that case, your total energy or your mechanical energy is 19,800 joules. And that stays constant throughout. That does not change. Doesn't change. So that's constant. And then to find your velocity, you take your kinetic energy equation and you manipulate. So you want velocity by itself, so you multiply both sides by 2, divide both sides by your mass, and you get v squared is 2 kinetic energy over mass. You want to get rid of the squared, so you square root, and you get velocity is the square root of 2 ke over m. And then you just plug in to solve for your velocity. That's about it for that one. I would look at 79 through 85. Those are some important key points. So I would look at 79 through 85. The key is on your review. Remember, conduction has to be touched. Convection is through air or liquid. Radiation, it can go through in the vacuum. It's like your electromagnetic waves. First law seems like the simplest. It's Two objects got to want to balance out. Everything wants to be equal. Your first law is energy cannot be created or destroyed. Second law is your law of chaos, so that's your law of entropy. Your third law is your zeroth law. So third law, everything wants to go to absolute zero. So there you go. Let's look at your waves. We have almost done. So we're looking at waves. Let's look at 88 and 89. Remember, longitudinal are parallel, and it's because we're looking at 88. So we have your so this is a longitudinal wave. It's parallel because the energy is going that way, and your particles are moving this, back and forth. They're vibrating back and forth. And 89, it's transverse, because again, the energy is going in this direction, but the particles are going up and down, so that makes it perpendicular. And this is parallel. Yay! I would definitely know resonance. So 90G, I would definitely know. If we're talking about a wave, so how many waves did I just draw? So remember, you go to crest to crest or trough to trough. So if we're looking at crest, we would count 1, 2, 3. So that'd be 3 waves there. So just make sure you count crest to crest or trough to trough, because that'd be 1, 2, 3. So either way, 3 waves. Yay! I would definitely know 96. That is your diffraction. Remember what's happening? That is diffraction. So I would know that that's diffraction. Basically, diffraction happens when a wave is having to be, pass through pretty much a small area there. So basically, because it's having to look, and remember it makes like a D shape. So if we have waves coming through, as soon as it gets this part, it's having to start to bend to get through the small hole. So I would definitely know that. Let's look at 97. So 97, you have a 10-meter long rope is used to create standing waves. If the rope makes 240 vibrations in 1 minute, what is the period? So remember, period is your T, so big T. So that's time over vibrations. So your time you want in seconds, it's 1 minute, so that'd be 60 seconds over 240, and so that just gets you 1/4 or 0.25. Your frequency is flipped, so that's your vibrations over your time, so that gives you 240 over 60. That just gets you 4 hertz. And then to get your wavelength, you have to do your velocity equals wavelength times frequency, and in this case, your velocity is 12. You're looking for your wavelength, you just solve for your frequency, which is 4. Since it's being multiplied, you divide. What you do to one side, you gotta do the other. So therefore, your wavelength is 3 meters. You just recently did that, so you're good on that. Looking at 98, remember that your sound waves are mechanical. So basically what that means is they're actually physical vibrations. You can feel it, touch your throat while you talk, you can actually feel it. So sound are actual physical vibrations. Y'all know I can't spell. So physical vibrations, physics, right? Physical vibrations. Kind of an example of that is, we've talked about how the different types of earthquake waves. So, there's actual, even though it's moving, compressing, and retracting like sound waves, like longitudinal waves, that's still a physical happening. Light waves is not necessarily physical. You can't really feel that dealing with light waves. Another thing is, when sound travels, it's faster in a solid and then goes liquid gas. So I'm looking at like 140 right now. So sound does affect when it's going through different mediums, either speeds up or slows down. Light does the same thing, going from like vacuum to our atmosphere. It changes speed. So it does change speed through your wavelengths, would then compress or get bigger according with how much that is changed. I would definitely know your visible light spectrum, your 170. I would definitely know that. So like which one, your radio waves has the higher wavelength, your gamma rays has lower wavelength, radio waves has lower frequency, gamma ray has higher frequencies. I would know I would know each one. One just know radio and gamma. I would know like infrared and visible and ultraviolet and X-ray. I would know like the in-between ones too, like which one's stronger. So looking at your electromagnetic remastery, those questions, you might see those questions. Dealing with light and sound, going back to like 104, dealing with light and sound, think about why like if we're dealing with like a sonogram when we're trying to see a baby, why don't we just use x-rays? Why do we use sound waves for that, not x-rays? Let y'all think for a minute. But x-rays, they do have some radiation. They do have danger. Remember, we have to put that big heavy thing on anytime we do an x-ray. So you wouldn't necessarily want to be sending radiation out to a baby. So your sound waves are not as intrusive because they don't have that radiation dealing with them. So I think that's it. I've done your key points in your review. If you want to look at the whole key to your review, it will be up on Schoology. Hopefully you have happy studying for your final. Have a wonderful 3-day weekend, and thanks and gig 'em. Good luck. Bye.